upper and lower bounds. Understanding bounds is an essential concept in mathematics, especially when dealing with rounding numbers. When you round a number to a specific place value, you create a range within which the original number could have fallen. This range is defined by the lower bound and the upper bound. The lower bound is the smallest value that the rounded number can represent, and it is part of the range. On the other hand, the upper bound is the largest value that the rounded number must be less than, and it is not part of the range. Let's see how to find the upper and lower bounds. First, determine the degree of accuracy to which the number has been rounded. This could be to the nearest whole number, tenth, hundredth, etc. Once you know the degree of accuracy, divide it by 2 to find the margin of error. For example, if a number is rounded to the nearest whole number, the margin of error is 0.5. Add the margin of error to the rounded number to calculate the upper bound. Subtract the margin of error from the rounded number to calculate the lower bound. The range between the lower bound and upper bound is the error interval, expressed as LB less than or equal to X less than UB. This interval shows the range of possible values the original number could have been before rounding. For example, if a number is rounded to 3.2 to the nearest tenth, the degree of accuracy is 0.1. Dividing by 2 gives a margin of error of 0.05. Therefore, the lower bound is 3.15 and the upper bound 3.25 is 3.25, making the error interval 3.15 less than or equal to 3.2 less than 3.25. Degree of accuracy may be given as a place value, for example, rounded to 2 significant figures, or it may be given as a measure, for example, nearest meter. Now let's see how can we determine the bounds of a calculation. To identify the upper bound of a calculation, think about how to maximize the result. To find the lower bound, consider how to minimize the result. For example, in addition, the upper bound occurs when both values are at their maximum. The lower bound happens when both values are at their minimum. At times, different bounds may be necessary within the same problem. Consider 2 numbers, x and y, such that their error intervals are as shown. Here, Lx and Ly are x and y's lower bounds respectively. Also, ux and uy are the upper bounds of x and y respectively. When you add x and y, add the upper bounds of the 2 numbers x and y so that we get the biggest possible value, which is the upper bound of the result, and add the lower bounds of the numbers to get the lowest possible value, which is the lower bound of the result. When you subtract y from x, subtract the lower bound of y, which is the lowest number, from the upper bound of x as it gives the biggest possible value, the upper bound of x minus y. To get the lower bound of x minus y, subtract the upper bound of y from the lower bound of x, because when you subtract a bigger number from a smaller number, you get a lower result. When you multiply the 2 numbers x and y, to get the upper bound of x times y, multiply the upper bound of x by the upper bound of y. And for the lower bound, multiply the lower bound of x by the lower bound of y. In the case of division, here, x divided by y, to get the upper bound, divide the upper bound of numerator, that is ux by the lower bound of denominator, that is ly. Also, to get the lower bound for x divided by y, divide the lower bound of the numerator, that is lx, by the upper bound of the denominator. That is uy, don't you remember that? Increasing the numerator and decreasing the denominator makes a fraction bigger, whereas decreasing the numerator and increasing the denominator makes a fraction smaller. We can apply bounds in real-life scenarios and to determine the level of accuracy of calculation. Let's see an example. A room measures 20 meters by 10 meters, where length is made to the nearest 8 meters and breadth to the nearest meter. Find the upper and lower bounds for the area of the room. To find the answer, first you have to find the bounds for each dimension, here for length and breadth. You could write these as error intervals, or just write down the upper and lower bounds. As the length has been rounded to the nearest 10 meter, the true values could be up to 5 meters bigger or smaller. That is, degree of accuracy is 10, and when it is divided by 2, we get 5 as the margin of error. Hence, for length, lower bound equals 20 minus 5, and upper bound equals 20 plus 5, which gives the error interval as 15 less than or equal to 20 is less than 25. And for the breadth, as it is round to the nearest meter, the true values could be up to 0.5 meters bigger or smaller. That is, degree of accuracy is 1, and when divided by 2, gives 0.5 as the margin of error. Hence, for breadth, lower bound equals 8 minus 0.5, and upper bound equals 8 plus 0.5, which gives the error interval as 7.5 less than or equal to 8 less than 8.5. Calculate the lower bound of the area using the two smallest measurements. A equals 15 times 7.5. Lower bound for the area of the room equals 112.5. Calculate the upper bound of the area using the two largest measurements. A equals 25 times 8.5 upper bound. For the area of the room equals 212.5. Hence the bounds of the area is 112.5 less than or equal to area less than 212.5. Let's see another example. A car travels 120 miles, which is rounded to two significant figures, in 3 hours, which is rounded to the nearest hour. Calculate the upper and lower bound of the speed of the car. We know that speed is distance divided by time, hence we need to calculate the bounds for distance and time. For distance rounded to two significant figures, degree of accuracy is 10 and error margin is 5, which gives the error interval as 115, less than or equal to 120, less than 125th now. For time, rounded to the nearest hour, degree of accuracy is 1 and error margin is 0.5, which gives the error interval as 2.5 less than or equal to 3 less than 3.5. Hence, to find speed, keep in mind the rule for fraction. To get upper bound, divide the upper bound of numerator, here distance, by the lower bound of denominator, which is time. And for lower bound, divide the lower bound of numerator, the distance, by the upper bound of denominator, the time. Hence, the bounds for the speed of the car in miles per hour is 32.86, less than or equal to speed less than 50. And that's how upper and lower bounds help us estimate values with precision. If you found this helpful, don't forget to like, share, and subscribe for more math insights. Have questions? Drop them in the comments. We would love to hear from you. See you in the next one.